India's population has crossed 1 billion people, and it is still climbing. To keep this many people fed, the country needs more than 250 million tons of grain every single year, just to survive. Throughout history, the solution to population growth was simple: clear more land and plant more crops. But India's borders are finite, and the land is already farmed as intensively as physically possible. There is no more frontier to expand into. We've tried brute forcing our way out of this before. The green and white revolutions drastically increased our grain and milk outputs, but those methods required immense amounts of water, chemicals, and land stress, pushing our environment right to the edge of permanent damage. We are out of physical space, and our natural resources are maxed out. Our only remaining option is to look inward. We have to scientifically optimize the biological limits of the crops and livestock themselves. The first step is upgrading the base code of the organisms we eat, what biologists call crop variety improvement. By crossing genetically dissimilar plants, scientists can force hybrid strains that contain the best traits of both parents. These aren't random mutations. These plots are specifically engineered to produce higher yields, resist diseases, and mature on exact timelines, so farmers can harvest them faster. This exact same logic applies to livestock. You take the rugged environmental resilience of a local breed and you cross it with the massive biological output of a foreign one. Take native Indian cattle, known as Bos indicus. They are incredibly tough and immune to many local diseases. By crossbreeding them with exotic dairy cows, farmers engineer a new animal that retains that toughness while producing milk for a much longer lactation period. But upgrading an animal or plant's DNA is only half the equation. You can have the most advanced biological unit on the planet, but if you put it in a poor environment, it will fail. To get high yields without destroying the dirt, farmers have to carefully balance heavy, nutrient-dense commercial fertilizers with organic manure to maintain the soil's structure and drainage over time. Then there is the spatial optimization, using a technique called intercropping. This is the practice of planting 2 or more different crops simultaneously in strictly defined alternating rows. Look at this diagram of the root systems. One plant's roots sit near the surface, while the others plunge deep into the dirt. Because they require different types of nutrients from completely different depths, they don't compete with each other. After the harvest, farmers use crop rotation. By planting a pre-planned succession of entirely different crops in the same plot, they allow the soil's moisture and specific nutrients to recover naturally over the year. By managing the geometry of the roots and the timing of the seasons, farmers extract maximum caloric value from the exact same square footage over and over again. The most extreme version of this biological stacking happens underwater in a system called composite fish culture. This diagram shows how scientists load 5 or 6 different fish species into a single pond. It works because the water is divided into 3 distinct feeding zones, and each species is biologically programmed to eat in a different layer. At the very top, catlefish are deployed to consume the food supply floating on the surface. Right beneath them, rohus dominate the middle zone, and down at the floor, mrgals and common carps act as bottom feeders. Every single calorie introduced into the pond is consumed, and none of the fish ever cross paths to compete for a meal. These integrated farming systems create massive synergies. For example, placing apiary boxes right next to an agricultural field allows bees to extract high-quality honey while simultaneously supercharging the pollination of the crops. It's biological min-maxing. You multiply your total yield simply by stacking non-competing natural systems directly on top of each other. But generating a massive yield is pointless if it rots in a shed. Biotic threats like insects and fungi, or abiotic factors like improper moisture and temperature, can wipe out an entire season's work. Before a single grain is stored, it goes through a strict sequence of defensive protocols: rigorous physical cleaning, systematic UV drying and direct sunlight, targeted chemical fumigation to eliminate pests. To safely warehouse millions of tons of biological material, you need infrastructure on an industrial scale to isolate the grain from the outside world. This meticulous defense is the final, non-negotiable step. It ensures that the math actually holds up, and the calories survive to reach the people who need them. For thousands of years, agriculture meant scattering seeds in the dirt, relying on heavy labor, and hoping the weather cooperated. Today, it is a precision-engineered biological framework. It's the active management of genetic traits, soil chemistry, and automated threat responses working together in perfect synchronization. To keep our food supply secure, we must advance this scientific intelligence, optimizing yields without degrading the Earth that supports us. To survive on a crowded planet, we can't just conquer more physical space. We have to learn how to hack the biological limits of the space we already have.